Hello, hello. Today we're going to be talking about tessellation, reptiles and fractals. I'm Tony Bearden, and you can see behind me, aiming high, there's the website where there's lots of resources for you. And I started AIMSEC 20 years ago. Caroline.
I'm Caroline Ainsley. I'm the founder of Bubbly Maths. The idea is that we make maths fun for make maths fun, enjoyable, achievable for every child on earth. What better way to do that than to work with Tony to provide fantastic activities that you teachers can use in class.
And Władek is with us, who's a colleague. Władek, please introduce yourself. Władek is from Poland, but he teaches in England.
Hello, everyone. My name is Władek Szczerba. I'm teaching at City College, Norwich, Paston campus. Yes, born and raised in Poland.
Okay, well, what is the program going to be today? Well, it was to help you to improve knowledge and understanding and skills in transformations. And these are translations, reflection, and rotation, of course. And we're going to be thinking about tiling and tessellation and how they're similar and how they're different, and the applications of those mathematical ideas, and about similarity and enlargement. Now, we always think in these workshops about a learning spiral from early years to leaving school. In fact, throughout our lives, but we're focusing as teachers on the time, the years, 12 years or 13 spent in school. And so here we start off at the bottom of, so we're numbering 1 to 11 upwards, not downwards, looking at something from very, very simple, which is called a tiling starter, that you can do with the youngest sort of 6, 7-year-olds. And then each topic there, I'm not going to read it, you can read it for yourself, is getting a little bit more suitable, a little bit more challenging, suitable for lower primary, upper primary, and finally lower secondary and finally the school leaving year. So what I want to say to you is that during this session, you probably heard me say it before, you need to wear 2 hats, the teacher's hat and the learner's hat. So just relax into the idea now that you're going to be a learner when you're doing the activities, and that'll help you as a teacher. I think if you're making your learners do something, you should have tried it yourself, and this is your opportunity to do that. So you'll have time to try some problems for yourself today. Others will be introduced, other problems that you may want to try later with your learners, although we'll not spend much time on them today.
At any point, there are activities during the video, so all you have to do is pause the video and do the activity and then come back on again. So tiling for young children. The experiences that young learners have, these are all building them up to being capable mathematicians and becoming more and more capable. And it starts as in the early years with pure experiences. So tiling, you can, if you use just the kind of the Z shape there, they can make these shapes. They can see if they can either by drawing them in or coloring them in, they can fill out. You've got a dinosaur and a camel, both very interesting to young learners. And they can see if they can make, these are called triominoes, those shapes of 1, 2, 3, 4. Sorry, tetrominoes, I beg your pardon, they are tetrominoes. They've got 4 squares, and see what shapes your learners can make out of those 4 shapes, out of the tetromino, that zigzag shape. And you can either give them challenges or get them to make their own. So what about if you use 5 squares or 6 squares? And now the important thing is that you can use, there will be no gaps. So that's a nice challenge in itself. Use square paper and make up your own templates. Now, great questions to ask are, what do you notice? How you can ask them, how many different tetrominoes can you find? How many shapes can you make out of 4 squares that will do the activity of tiling or tessellation, depending which way around it is, will fill the space. What shapes can you make out of 4? So tiling for young children, we've got, now there's some gaps in this one. So we're using L shapes now. So how will you use the L shapes? So the elephant, I beg your pardon, can be tiled with L shapes. So the question is, if they've thought about what tetrominoes are possible, what shape tetromino would you make the robot with? What shape would it have to be? And that's a really nice challenge for them. And then you've got the penguin. Will that be, is the robot a different shape to the elephant shape, which is made with the L's? What shape would you have to use to make the penguin? Now, you're not filling in the dots, you're not filling in the eyes of the robot and the gap in the arm of the robot or the eye of the penguin. How would they make that? And of course, then make their own ones.
The clue is, of course, those eyes. So you've actually got to have your tile that goes round the eyes. So the first puzzle is, what do you use? Is it an L shape, or is it some other shape made with 4 squares?
Yeah, a great place to start is the head of the robot, but give them a chance to have a go first before you give them, you don't have to necessarily give them a clue. They might work it out for themselves, but they need a clue. Start with the head of the robot.
And they can colour each tile a different colour, or at least the ones that are touching should be different colours.
Each 4 tiles, each tetromino different colour.
Well, each tile could be a different color. Each tile, whether it's an L shape or some other shape.
Okay, sorry, you're saying that the tile is a tetromino, right? So you're referring to, which you should be, and I wasn't. So the tile is whatever tetromino shape you've chosen, and then you're coloring in each one of those a different color. Okay, every set of 4.
So we've supplied a worksheet, which if you haven't already printed it, you can print it after this session. And that you can print part of it to give your learner. So these shapes you can print out and give it to your learners to fill in, to color in, or they can use an L shape and draw around it to fill up the elephant. It's quite a big job to do that. They might do it in a group. So Escher, the artist, was born just at the end of the 19th century, very famous artist, and his work was very mathematical, and that's why we're going to show some of it today. So we're going to be looking at the connection between maths and art. Now, as a young man, he traveled around Europe and he visited Spain, and he was very much influenced by the work of the people from Africa, the Muslims who'd brought over all their knowledge from Africa about 600 years ago, and built some wonderful palaces and mosques in Spain and decorated them with Islamic art. And when Escher saw that art, he saw that it was very mathematical, and he was absolutely fascinated by it. And he devoted his life to his art, which was exploring mathematics when the patterns and if you were to go on to university to read mathematics, you'd learn about something called groups, which is what defines and explains these patterns. But your learners can see transformations in these patterns. So this is Islamic art from the 14th century. The arches you see there are inside the Alhambra Palace, and below, look at those froggy pictures. They've all got creatures that are like lizards or frogs. And if you look at this one in the middle, and you look somewhere, if you see where my cursor's pointing, it's the cheek of 3 different frogs. So if you take the point, there it is, that's the point. You see my cursor showing you. You can rotate this round by 120 degrees, and the pink frog goes to where the yellow frog is now, and the yellow frog goes to where the green is now, and the green frog goes to where the pink is now. So you've got rotational symmetry there. And you can see again, this is another tiling of different shapes. And in this wall and the arches and around the windows, you can see lots of art. We'll see some more.
So we've got a different kind of feature here where these are frieze patterns. So these are when you might see them at below a roof, where you've got a pattern that repeats laterally or vertically. You might have a vertical, or it might be a ribbon around the edge of the room. Quite frequently it's either just below the ceiling or maybe halfway down the wall, and the pattern repeats. It's called a frieze pattern. And so spot the pattern, have a look carefully at this image and spot the pattern that repeats. And think about the symmetry there. Think about what's happening. We've always got, with a frieze, you've always got translation. So the pattern repeats using translation. But there are other things that are repeating here. And there are other transformations that can cause them to happen.
So this is also called a frieze pattern. Another name for it is a strip pattern, so that it is actually in one dimension. So it doesn't cover the whole wall, it just covers a strip. And these frieze patterns are used very widely in decoration.
So these ones are Persian frieze designs. Now these have been handcrafted, so they are not absolutely identical to each other, but they are supposed to be. The idea is the pattern repeats. Some of them are more simple, they're kind of more clear cut, because the other ones, there were rotations and things happening as well, and glides, but these are quite simple. They're just almost just the same pattern repeating. We could cut one out and repeat it very simply like that.
I think if you look, you can see vertical lines of symmetry there, with what's on one side of the line is the same as what's on the other side of the line.
Now this one's from also a frieze, again handcrafted, so they're not absolutely identical, but they are supposed to be the same.
This is more than 2,000 years old. It's from Greece, and so I think the wall of which it's part has subsided a little, so it may have been more regular.
Here you have something that we see that we ourselves create. So with tires, you can see the repetition in the tire tracks. Footprints are also, if you let's say keep them in a straight line, they're also free. Is the same principle. They use the glide principle, where you see you've got alternating. So you've got other symmetry, other different types of symmetry, looking at that, and you can make your own. you can create your own symmetries, and you can have your learners create using their hands or their fingertips. You can use thumbprints, whatever you want to make different symmetries.
I think it's interesting to think about these footprints. So as the footprints, there obviously there's a translation that's going forward along the direction the person is walking. But if you stand with your feet next to each other, they're symmetrical. So there is, as it were, a symmetry, a reflection of one to the next. But this is what's called a glide reflection. So this is the left foot and this is the right, and it's not now a reflection of the right foot is not a reflection of a simple reflection of the left foot. It's what's called a glide reflection. So what makes up a glide reflection is putting together a reflection and a translation. So a reflection and a translation makes a glide reflection.
And you can get your learners to actually draw that out. So start with one foot or one hand, get them to draw the line of symmetry, get the reflection, and then work out the translation. And so they themselves will be creating glide symmetry, which hopefully will solidify the idea with them.
So what we have got is just a strip or a frieze, one dimension here. And there are 7 frieze patterns possible, no more, only 7 in the whole world. And it doesn't matter, thousands of years, people have been making these decorative frieze patterns. They've only ever been able to find 7 frieze patterns, and it can be proved mathematically that there are only 7. So how do we define them? We define them by the transformations that are combined to give the frieze pattern. Now, there are countless different motifs. You see some examples here, things that look like commas or feathers or bows or flowers. And also the same frieze can be done with letters of the alphabet, as you see on the right there. So it's the transformations involved that define the patterns, not the motifs. So we're going to go one by one through these and think about how that pattern is, what transformations make the pattern. Okay, this one is, whether you look at this square with a piece threaded through it, or whether you look at P, 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 P repeated, something's happening to go from one P to the next, to go from one square to the next. So that is one of the transformations. And what else? Can you see anything else? Can you see any reflections or rotations here? No. All you've got is translations. So that's a very simple pattern that only has translations. What about the next
one? Within the repeated pattern, there is no symmetry, because the one is, well, in the one you were looking at.
Here, can you see any other symmetry? Of course, you can repeat the pattern by translations. That applies to them all. But can you see any rotations, or can you see any reflections?
So you're looking for symmetry within the repeated pattern, as well as how the pattern repeats.
So here again, translations, and here's reflections in a horizontal line. So if you look through the middle bar of the E, the top and bottom are images of each other by reflection. So you can reflect the whole pattern and it will still look the same. You can reflect it either in a horizontal line through the middle of these, the pattern shown, or along the middle bars of the E's. So that's the second most simple pattern. What about this one? Characterized by DB, 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 DB. Now here the frieze is D with B. And then it repeats dB, and then it repeats dB. So can you see any reflection here? Is the left-hand side of that motif the right-hand side, same as the right-hand side? Or is the top the same as the bottom? Well, clearly the top isn't the same as the bottom, so there isn't a horizontal reflection, but the left-hand side is the same as the right-hand side. There are lines of symmetry. I'm showing you the lines of symmetry with my cursor. Now, if you reflected this whole pattern by this line going down the middle, what's there would reflect over to here and vice versa. You've got each motif has a line of symmetry. The whole pattern has a mirror lines in it, vertical mirror lines in them. Now here the motif is PD with the letters, PD again, and here is there a horizontal line of symmetry? No. Is there a vertical line of symmetry anywhere? No. What could there be? Look at it. Now here, these are good discussions for your learners. Get them to discuss what transformations they can see. And if they name a reflection, get them to show where the mirror line is, axis of reflection. If they say there's a rotation, get them to show where the center is. And I'm showing you here where the center of this rotation is. There's a half turn or 180 degrees rotational symmetry of this pattern. You can rotate the whole pattern about this point, which I'm showing you with my cursor. And of course, each motif, PD is a motif, you can rotate that about points that's in the middle there.
Also choose different points of rotation, let's say the center of the eye of that feather, and then translate it.
Yes, you've got the translation, and if you choose a point, you can rotate about it through 180 degrees and repeat the pattern. But you've got to choose the centers. Now here, HHHH in a frieze pattern, we'll see this later in a three-dimensional tiling, but this is not a two-dimensional tiling. But this is a one-dimensional tiling. It's just a strip. But what can we see in this? What transformations can we see here? Can you see mirror lines? Can you see a horizontal mirror line? Can you see a vertical mirror line? Or many, actually. And is there any rotational symmetry? Well, here you've got a lot. There is rotational symmetry. I mean, if you put your point, if you hold down the point that I'm showing you here, right in the middle of the thing that looks like a bow, you can rotate it by 180 degrees, and it will then repeat, the strip will repeat itself. So you've got reflection as well. You've got reflection in a horizontal axis. You've got reflection in vertical axes too. So if you go halfway between this pattern, in the middle of this pattern, the right-hand side and the left-hand side are images of each other. So you've got reflection in horizontal and vertical mirror lines, and they give you the rotations. That gives you rotations. Now, what about this one? Now here the motif is PB. What do you see here? You might think there was a reflection in a vertical line between the commas here, but since this tail is on top and the other one is behind, there is no vertical mirror line here. But what do we see? What do we see here? Ah, that's like the footsteps. So can you see this is a glide reflection like the footsteps? So here you move the shape along and reflect it. And the two give you, those two transformations give you a glide reflection. You've also got rotations here. Again, what about this one? Look at it, make up in your own mind what transformations there are. Think about it. What transformations are there? Decide for yourself. I'll show you in a minute and you'll see if you were right. Oh, this has got the lot. It's got whatever you thought it was there. There's translations, there's a reflection in vertical mirror lines, there's footsteps reflections, like glide reflections, and there's rotations there. So, I mean, for example, if you take this as your center of rotation, you can be rotated by 180 degrees. So you've got everything there. So what we have...
There's...
Do you want me to go back, Caroline?
No, I was going to talk about the next slide.
Okay, go on.
So there's a difference between tilings and tessellations. Tilings, you are covering a plane. That's what you get on any floor that's completely covered. And it can be copies of a geometric shape. It's got no overlaps, it's got no gaps, it's tiled. In a practical world, if there's a gap in the tiles, you could trip and fall. So it's got to be covered completely. Tessellation is also tiling, but it's a special case. It has to fill the space with a regularly repeating pattern. So if you think of a floor, you might have a margin around the tiled floor. Well, that part is not part of the tessellation, but you could have a tessellating pattern within that. It has to be a regularly repeating pattern, and it has to be tiled, therefore covering the whole surface as well. Did you want to add something to that, Tony?
Oh, only to say actually that this picture here, which is called Day and Night by Escher, if you look at the white birds, they seem to be flying with a sky behind them with stars and the moon. But if you look at the white birds, that's the white birds. If you look at the grey birds and you see one picture, and if you look at the white birds, you see another picture.
It's like an optical illusion.
Well, it's hard to, it's a very clever tiling, but it isn't a tessellation because it's designed to be just contained in that square and not to spread out in all directions.
Whereas the lizards could go on forever and the pattern would keep repeating. So there are, just like there were, I think 7 frieze patterns, there are 17 wallpaper patterns. So now we're covering 2 dimensions, we're going up, we're going across on a flat surface, but there are only 17 tessellations, and there you can see them all there, and they've actually got the ways of describing them are written on that slide. And I mean, this has, mathematicians have worked on this, and they have proved that there are only 17 types of patterns. 3D, on the other hand, they've worked out there are 230 different patterns. Now, the 2D is usually used wallpaper on the floor, just repeating patterns going out, and this is not, repeating patterns going out in 2 dimensions. 3 dimensions occur naturally in nature, in crystal structures. So going into tessellations in 3 dimensions is useful for scientists, crystallographers. One would imagine that people looking for new ways to make not silicon chips anymore, but integrated circuitry for computers, smaller and smaller and smaller. can imagine they use crystalline structures, what knowledge about that for that. They
Well,
use it.
all materials, how
Yeah.
they how things fit together in whatever the material is really important in science. And to go back to the wallpaper patterns, this is clear that the Muslims who came over from North Africa were far more highly educated in 600 years ago than the Europeans at the time, and they understood the mathematics, but they understood there were only 17 wallpaper patterns, and they're all to be found in Alhambra, that palace that I showed you earlier. So there's huge amount of
All 17 are in the Alhambra.
oh yes,
Oh,
definitely.
right.
And,
I didn't know
it's very clear that the artists at the time understood that there were 17 and took pains to show them all. And so they understood the mathematics behind it. And the mathematics is actually at a much higher level than anything you do at school. The mathematics I'm talking about is to prove that there are 17 wallpaper patterns and no more, and that there are 230 different crystal structures in 3 dimensions. There's something called group theory, which people study in university mathematics at that level. So we're going to move on to doing something more about tessellation and tiling. So what do you see in this picture?
I see an angry bull.
It's
Lots
been
of them. Lots of angry bulls. I wouldn't want to get that close to real angry bulls.
well, it's been drawn by hand, but let's assume that the bull's heads are identical but not symmetrical. I think if you look at his eyebrows, you can see they're not symmetrical. So add it, imagine adding another bull's head and another one. Could you above the horns at the top, could you fit in the cheeks and the mouth and the tongue of another bull on the top of each one? Could you spread out? So could this be an infinite pattern that goes on forever and ever and ever of these bulls' heads? Could it cover a large wall and beyond that? And if you look at these coloured lines that I've put in, what you see is how you move. Just as we looked at it with the strip patterns, we're now looking at the transformations in these tiling patterns. And you can see the blue lines, the coloured lines help you to see the transformations. So there is a translation along these lines, and as you see, they join the corresponding points. So the nostrils of this bull, that's what I've joined with the green lines, and with the orange lines I've joined the top of their left hand, or on my side left, but as far as
Right hand.
his right horn, yes, those tops of the right horns are joined up with the orange lines. And that is that gives us translations in 2 directions, up and across in 2 directions. And it makes a parallelogram. So that's what we call a period parallelogram. So you see how that repeats itself. Now, on a squared paper, if you draw a tessellation made with an H shape, what would happen? If you've got some squared paper there, have a go at it. Or if you're watching this on a video next week or some other time, then get yourself some squared paper and make your own tessellation with an H. Now, we did see a strip pattern with H's. This isn't a strip pattern I'm talking about. It's a tessellation. it's going to cover the whole wall with no gaps at all.
And go on forever. It can
And
go on.
go on, and it's possible, you can see it's possible to keep on repeating it, and it should go on forever. Now I've put little black dots on corresponding points there, and if you were to join those points, what would you see? The corresponding points are at the top of the middle bar. Sorry, the top of the bar of the H on the, but on,
Or the bottom right hand side of the H. You can look at it that way. Bottom
yes,
right hand side of every H. You can put a dot on
bottom
those.
right hand side is a better way to characterize it, I think, Caroline. Yes, bottom right, but it joins two other H's at that point.
Yeah, but if you put a dot on the bottom right hand side of every H, then you've got the dots you need.
So join the dots. What do you notice?
Have we seen this before?
Right. So what you see is another parallelogram, and you see that the H is this H here that I'm showing with my cursor moves up, and it also has to move across a bit, and so this H also moves across this way. So the whole thing is moving. What's inside that is moving into what's inside that. But when you put them all together, each one is identical and is a period parallelogram with showing it moves with translations in two directions. Now, if you see what else is on this slide, you'll see there's a half H. So supposing the motif hadn't been a whole H, but had been a half H, could you have made the same pattern? What do you think, Caroline?
I don't think I need a half H.
You don't?
No,
What would you have?
what you just put up there. One
Oh,
quarter of the H using symmetry can create the H.
but you see, there are three different sorts of pattern made here that look like the H tessellation, but the one that Caroline was talking about with a quarter H has much more. It has reflections in two directions, and as well as the translations. Now, if you start with the whole H, you get this pattern. Well, you get the same pattern anyway, whichever one you start with. But if you're analyzing it as to whether there are, what it's got in it, then it depends on the motif that you're picking out. So just to put those two together, the bulls and the H, the two tessellations are based on repeating parallelograms, repeating by translations, and the H tessellation could be based on reflection of a half H in that dotted line that you see, or it could be based on rotations and reflections of a quarter H, and then all those are followed by translations.
So this is an activity that you can do on the worksheet. The simplest way of doing it is to, if you see the little bits in the middle, just all the little quadrilaterals and the little triangles, and then that partial H shape, print that out or copy it and then cut it up. And then what you've got to do is make it into a puzzle, move it around, and then you've got to create the H. So that's an activity that you can do with your learners, and it takes 5 pieces to make the parallelogram.
This piece moves over to there. This little piece goes on the top there.
Goes on the top.
That piece that piece goes into the cup shape there, and the other piece, this piece, goes into that arch shaped there. So that piece goes to there, this piece goes to there, this one goes there, and this one goes there.
And you end up with
Solid. All that would make an H, but actually in a period parallelogram, which then moves along its edges. So every single tessellation is moved in two-dimensional space by two translations. And if you see the parallelogram moving, it's not so clear when you just look at it how it makes the H. But when we convert one to the other with this puzzle, we can see that the H can move, but if it doesn't move. The H appears to move sideways and up and down. Anyway, that's the tiling.
So the next slide is about reptiles. Now, we're not talking about cold-blooded creatures that live in water or lizards or anything like that. We are talking about a repeating tile. And this one is an example, and it's called the Sphinx, kind of for obvious reasons. And it's a shape, a reptile is a shape that can be dissected into smaller identical copies of the same shape. So a challenge you can give to your learners is, you can see the solution right here, but you simply give them the bigger shape empty or with just the outlines of the triangles, and see if they can actually solve that. You can see where one of the solutions is the green, the yellow, the red, and the blue in that way round, and see if they can find any other ways that it will work. But you only making the same shape out of the shape that you start with.
And you can
go on.
Well, you can see that going from the gray one to the big one, all the lengths are doubled. So that's an enlargement with a linear scale factor 2. And the area is 4 times. You fit 4 of the small ones into the big one.
Yeah, and that's a nice simple way of seeing that by doubling the edge length, scaling up by a factor of 2 in length, you are quadrupling the area, and you can see it very visually. You can simply count the triangles if you need to. And this is called a rep 4 because 4 of the original shape, the original reptile, makes a repeat of itself, scaled up repeat of itself. Now, reptiles make fractals. You can see this one that's made up of regular hexagons, and these are lovely animations which you can get on Wikipedia. A lot of the animations and a lot of the content that Tony has obtained from Wikipedia, and it's a great source of lovely ideas for your classroom. And we're going to see something very interesting about, they look like footballs there, don't they, when they get smaller like that? That one in the middle looks like a football.
So a fractal is a mathematical pattern that has within itself smaller copies of the same shape and smaller copies within those smaller copies. So here you'll see the red and then the green and then the yellow, then the blue hexagons. And the patterns get smaller and smaller, but they keep on repeating themselves. That's a fractal. Now, polyominoes are shapes made up of squares. There are 2 squares that are called a domino, and there's only one way that you can make a domino. A triomino, well, there's more than one shape that you can make with 3 squares. Well, I should have said, the edges of the squares have got to join along the whole edge. You can't make like a brickwork pattern where, you know, the one square is attached to the others by sort of going halfway across two other squares. They've got to be joined edge to edge.
There's no glide, transformations here.
That's true. Okay, now this is a tetromino, but you can have that. You can have a T shape. You know, this square could be here, and there's more possibilities. Okay, and then this is a pentomino, 5. This is a hexomino, 6, but it's just one example. And our friend that we've had several times this afternoon, this is an septomino, that it's made, this H is made up of 7 squares. So there's a table here that shows how many of each type there are. So there's only one domino, but when you come to hexominos, there are actually 35 of them. Now, a good challenge for a group would be to find them all, you know, shade them on squared paper. Can you find all the different ways you can make a pentomino? Can you, there are 12 of them. That's not too great a challenge.
And it doesn't have to be done in one session. It could be done over a period of time, and they can be maybe a poster, and they can come in and think, okay, whenever somebody comes up with a new one,
yes,
it's a cause for a celebration and keep the interest going.
We'll come back to pentominoes because there's another puzzle with pentominoes, which is great fun to do. Now here, what you see is an example of a fractal. So remember I said a fractal is a shape which has within itself many copies of the same shape at smaller and smaller levels, and that process can go on forever. So inside this triomino, you can put 4 triominos. You can easily see how that's done. But if you can do it for one that's that size, you can do it for one that's that size. And so inside this triomino, you've got 4 triominos. But you can repeat that process again and again and again, and you can see how it's quite hard to see what's there when you get to this scale. And these are stages 0 to 5 of the fractal process based on the shape made up of 3 squares. Process which we call iteration. Repeating.
And we can see the fractions, the fractals using that, and these are simply animations. This is an animation of the triomino that Tony just showed you. But using the power of computing, you can find these on Wikipedia, and you can see how they work. Now, this other one is also a triomino. If we wait for it to repeat, now that's how it starts. So you've got the blanks on the top right and bottom, and as the fractals get smaller and smaller, you can see how the pattern evolves, and it looks completely different, but it's made from a repetition of the same shape again and again, and those are just both made from triominos. And if you notice, you've got the 4 colors in one and 3 colors in the other, and as they get more and more and more detailed, the 3-colored one on the right ends up as just white. The one on the left has an additional color which interferes with it slightly, but you've just got the 3 prime colors on the right, and with light, the presence of all colors, the 3 prime colors are in plain English, blue, red, and yellow. The presence of all colors makes white, which is the opposite with paint, but with light, the presence of all colors makes white. And hey presto, there you have it, as it gets into greater and greater detail. the
So
pattern.
all those colors are actually in the pattern, but our eyes can't see them when the spots get very small,
Yeah.
and we just read it as white.
Yeah, because they're combining those three colors together, and our brains, yeah, read them as white. So this one is one of my favorite shapes in the whole wide world. It's an iteration. You're starting with that shape, again, triominoes. By starting with that particular shape, you end up with a Sierpinski. Well, now we've got Vashwa, not Vashwa. We've got Władek with us, and Władek has a very special story. Do you want to tell us yourself, Władek?
Well, Wacław Sierpiński was working in the same field as my father some time ago, and they were working on fractals together some time ago.
And this particular fractal is named after, you say it in Polish,
Wacław Sierpiński.
Wacław Sierpiński, and this is a very famous fractal, and Władek, that is one of our collaborators, it was his father worked with him, which is, I find, extremely exciting. But as you can see, this is just made from a triomino, repeating the same pattern again and again and again.
Polyominoes. So what you have to do here is put 4 copies of these shapes together to make an enlarged copy of the same shape. Okay, 4 copies of the tetromino, L-shaped one there, to make an enlarged copy of the same shape. Now you can do that on squared paper by, outlining the L shapes, or you can do it by coloring them in, or you can do it by cutting out an L shape and then drawing round it to make the 4 copies that make an enlarged 4 copies of the single one that make the enlarged copy of the same shape. And then you can do the same with the pentomino again. So we've looked at examples where we're putting the copies inside, and if you can do it inside, you can build them together to make an enlarged copy with the area 4 times, or you can put the copies inside the outline to, like we saw with the Sphinx, to shrink it by a factor, area factor of 1/4. And there's the solution. Okay, so what we've shown in the diagrams I've just revealed is how you put 4 L shapes together, tetrominoes, and you can make a bigger one, or 4 pentominoes together to make a bigger one. Nice puzzles for your learners if you copy them and they cut them out and then reassemble them. Even when you've seen it, well, when you've seen it may be you can remember what you've seen, but sometimes once you've separated them, it's hard to put them together again. Now, this can be repeated again and again, infinitely often, to produce a fractal. Now, here's a challenge. Now, there's some squared paper there, and you can take 1/4 of that area of squared paper and repeat those octominoes. They've got 8, those tiles are made of 8 squares. And what the best way to do it is to put 2 copies together to make a rectangle. And I think it's easy to see how that can be done. And once you've got a rectangle, then you can keep repeating that rectangle. So you can have a go at that one. So can you make 4 tessellations with these octominoes? Shown. So in each case, you've got 2 octomino tiles that make a square. The red and the green are obviously identical shapes. And once you've got the square, you can then easily repeat it. So these are very easy to make once you see that 2 of those make, 2 octominoes make a 4x4 square.
So these are fairly simple puzzles, but the conversations that, especially people work in pairs or in groups, the conversations that they'll have around it, and the transformation language will automatically come out, is very useful as solidifying ideas. And
it's also something that the learners enjoy very much, which is a good thing.
which is the principle behind all of these activities. Especially Tony is making an effort to give you activities that your learners will enjoy. We're going to go away from squares and rectangles. Oh, again, yeah, as it's popped up, you can make these copies smaller and smaller again and again, infinitely often, to produce fractals. Each and every one of these will do that we've been working on. Going away from rectangles and squares, we've got rectile trapezia. So just as you had the challenge of making repeating shapes with octominoes, now give you the clue, you can make all of these 3 trapezia using rep 4s. So each one of these, you make 4 shapes that are half the length, that scale them down by a factor of 2 in length. 4 of each will fit inside and make that shape. So the challenge is to do that. It's a puzzle. We're not going to do it right now, but it's a very it's a nice puzzle for you to do, and a great one for your learners. And we've got the different language. We've got the trapezium now instead, and if you can repeat this down, you can make again fractals out of it. And there are the solutions. There might be more than one solution, or there might not be.
What's nice about this is I think you can see that you can fit the 4 shapes inside the outline of one, and you can keep repeating that and go on forever, infinitely often, although actually, practically speaking, once they get very small, they're too fiddly to, you know, but you can imagine them. In the brain, you can go, with mathematics, you can go to places that you can't actually achieve in reality, but it's a reality. It's a reality. The limiting process, it gets smaller and smaller. It's a reality in mathematics, and of course you can build it outwards too.
That's a wonderful thing that mathematicians do, and you want to encourage your young learners to do that. They don't have to become professional mathematicians. It's not about that. It's about training them to be thinking that way. It's always what if. What if it was smaller? What if it was adding dimensions? That's something mathematicians do all the time. Okay, that's in 2 dimensions. What about 3? What about other dimensions? And this is expanding it and thinking about, okay, what other shapes can we do this with? And are there any other kind of reptiles, Tony? Oh my word. Okay, so over here, all right, so what we can do some spotting. Can you spot a rep 2? Can you, which ones are rep 2, which ones are rep 3, rep 4, rep up? What about rep 9s? What have we got here? We've got a shape that's like an L shape made of lots of little ones, but actually, what are they? Do they have to be? Do you have to have that many, or are there? You've got to interpret them. I mean, I think I'm looking at a rep 3 rather than the. I don't have to count all those little squares. And Tony's pointing out with arrows some rep 9s, rep 2s. And then we had a challenge. We've got a fish there. So they can still fill out the plane by putting the fish together, but you have that translation, or you have the glide effect, the footsteps effect, using the fish, and you've got the 4 squares at the bottom. Again, you've got the symmetry and can be repeated on the bottom left there, and but it doesn't necessarily have to be a solid. To start off with a shape that's a homogeneous shape.
I think you can see with this fish at the bottom here how you can fit another fish just exactly the same by putting, you know, this side of the fish in here, and
Yes.
the Escher type picture you could build up.
Yeah, so you'd have them right on top of each other, and then you've got that same thing again just to the right, but without being where they're overlapping, without overlapping the tiles, but they're overlapping. Yeah, you don't go all the way to the end. You'd fill in the blanks, and it works. It tessellates.
Ah, now Caroline, oh, these two other fish there. Yes, I've just
Yeah,
pointed.
you've got the fish, and then to the left of that, you've got the 4 squares that are staggered. So you can still fill that plane again by translation, or you got basically the glide effect, the glide transformation there. We're back to my Władyk's friend Sapinski. So this is a fractal. Now, as a reptile fractal construction, you can each one, like the one that you're seeing on the right, can be shrunk down to the extent where it actually fits into one of the teeny tiny triangles of the one on the left. So that's how and each one of those teeny tiny triangles could have the whole of the one on the right shrunk down. But going the other way, 3 of the one on the right makes the larger one. So in 2D you need 3 identical ones. I guess it's a rep 3, Tony, Sapinski gasket. I hadn't really
What you've
thought
got
about.
here is this is 3 of these triangles make up that one, but of course you can do 3 smaller ones inside. So, for example,
Now you
this
start with teeny
one has
tiny,
got
yeah.
3 smaller ones inside it, and this one has got 3 smaller ones inside it, and so it goes on and on.
But this would be a rep 3 though, because you're starting the basic
Yes,
building block has got 3 triangles,
yes.
and on the 3D level, the basic building block has 4 pyramids or tetrahedra. So, but this would be a rep 3. I hadn't actually continued the thought and actually gone to that. But but this one doesn't it's a fractal, but it doesn't tessellate the plane.
No, no, it doesn't. It's still, yeah, I've introduced this as a reptile, and I think it's fun. We link it up with a lot of mathematics to the Sabinski triangle, a lot of simple mathematics too, areas of triangles, lengths, and perimeters. A lot of mathematics.
And purely the concept of scaling, just getting familiar with the concept of scaling, and something that a lot of schools have engaged with is everybody makes a triangle or makes a stage of it, and then everybody writes their names or decorates it in whichever way they want, and then they all stick it on a huge wall or on the ground, and they make a huge display, and they make it as big as they possibly can, and that's very engaging. It's a lovely activity. And lots of conversation around it.
So this is a carpet. It's what it's called, a carpet. And it's made of 8 copies of itself. So they're all in different colors. But then in that, there's 8 smaller ones within each one. And so it goes on and on. It could go on forever in your imagination anyway. This is another fractal. And there's a lot, I put these in with some links as to how to find it for yourself and find some more ideas about these. At the higher level of mathematics, there's a lot. About 30, 40 years ago, this became a very active area of research in mathematics, this idea of fractals and repeating the repeating pattern that goes on and on and on, repeating forever. So I thought I'd just put that one in for you. And now, how about you actually being creative yourself, and or your learners doing this, and making your own Escher type tiling. So this gives you a little bit of guidance about how to set about doing that. So you make some sort of cut out of one edge from one corner to another in the shape in a square, and it here I've just shown a trapezium, a bit boring. So you touch that onto the opposite edge, and you get something that begins to look as if you could make it into a cat's face or something. But why not? You don't. This doesn't have to have a straight edge either, because once you have got it repeated down here, you could add another one that was identical and make a tessellation.
And
And
if you build it out of card, you're making a template, and then you can just keep repeating it.
now you don't actually have to go from corner to corner. You can just cut a chunk out here, and then attach it on the other side. So
Could you go
because
diagonally across, like make a little wiggly line just diagonally across, and then that wiggly line repeats itself because you're using that as a template.
yeah, so if you look at some of the Escher's pictures of birds or fish or frogs or just shapes repeating themselves, you'll see that there's a huge potential there, and you might like to just play with that. It could be done in an art lesson in primary school, for example, and maths and art coming together beautifully there.
Really, definitely. Great conversations. So you can go back and see lots of the other videos that we've done for the G10. We've done Happy Maths Hour. Tony and I have been making videos since the beginning since COVID started. And the resources on the Aiming High website, Tony's been working on since, well, all your teaching career, which started in 1962. Tony's only 25, so she's looking really good for her age. Time warps. So we've got the YouTube channel. If you just search for Maths Toys with No Gap, and you'll find our YouTube channel if you're not already on it. If not, go, and if you're on it, then search for other topics. And now on our Facebook.com, on the AIMSEC essay, you can see it there. There is an activity every single day of the year. And Tony posts them, and she does that automatically. We've worked out how to do that. I think we might be the two oldest YouTubers on the planet. What do you think, Tony? I think we should search for two older YouTubers than us. But Tony writes them and posts one, and automatically, and then I have to do, even on Christmas Day, which is a holiday for me, every single day of the year. What the Americans say, 365, whatever. Every day there's an activity for you that you can take and you can use in your classroom. And even if they're higher level activities, if you click on, remind you to go onto the Aiming High website, there'll very often be an activity, an equivalent activity, just to give a young learner an experience that will start building up their mathematical thinking ability. And for this particular video, you've got all those links to activities with much more information, help, and again, links. There will be links within those to other activities and teachers' notes, and many of them have inclusion guides. So you've got, again, guides to cover all levels, and starting at the really young learners all the way to high level maths, or at least high for me.
So it's time to say goodbye. Goodbye from Caroline and me, and Radek. Thanks for coming to the workshop. Please use AIMSEC ideas from the Aiming High website. And if you do, register on Aiming High and then add comments. We'd love to have comments from you. Share what you've learned with other teachers and try to help all your learners to have a yes, I can attitude to mathematics, not a, oh dear, mathematics, I don't think I can do this, it's difficult, but a yes, I can. It is difficult, but I'm going to try, I'm going to keep trying until I succeed.
And if you can do maths, you can do anything.
Thank you very much, and it was a pleasure to be part of this. I'm really hoping to see more and more teachers involved, and hopefully we can improve the culture. Yes, I can.
Yay! Władek's a wonderful facilitator, so he is definitely a yes, I can person.
Yes, thank you, Caroline, and everyone here. We are so grateful. It's improving, and even on us, we are becoming better and better teachers through these workshops. And yes, I can on the learners, it's increasing.
Yay!
And it's great. Thank you very much.
Thank you so much for participating, Noko.
Thank you, everybody, and we're going to say goodbye.
See you next time.
Bye-bye. Thank you.
Bye.
Bye. Oh, we got a heart from Tobeka. Thank you. Bye-bye. This is a Global Teacher Empowerment Network video collaborating with AIMSEC and the Aiming High website. Our mission is to benefit children in disadvantaged communities all over the world by empowering the teachers who teach them mathematics.